Both ways, yeah.
This may be the Italian version.
Angelo is Italian. Angel is here. So Angelo is Italian and Hansen is son here. Who's born here, so it's Angelo.
Good, so let's get underway. And Guido Bellomo will be telling us about the relative character of quantum correlations. Over to you.
Thank you very much. So, first of all, I would like to say thanks to all the organizers, especially to Olympia and Sebastian for their help with my talk. As you can see, I'm going to talk about the relative character of quantum correlations. Relative is said in a sense that will become clear as we go on, I hope so. But maybe it can be thought as a generalized perspective to understand entanglement and discord. So, okay, this one is probably the least original way to start a talk about entanglement, but I think that we have enough creativity in Jeffrey's talk the other day, so I feel free to cite Schrödinger. You know this quote when he said in one of his famous 1935 works that the best possible knowledge of the whole does not necessarily include the best possible knowledge of all its parts, even though they may be entirely separate and therefore virtually capable of being best possibly known. So this idea will underlie all our discussion, our present discussion. The problem we're going to tackle here is that quantum correlations are relative to the non-unit substructure of the quantum system. And so there are two main questions here. The first is, does this relativity imply some kind of ambiguity in the notion of entanglement? And what are consequences, if there is any, arise from this relative nature of quantum correlations? Our plan is very simple. I will start by reviewing the usual notion of entanglement as it is usually presented in the physics literature, and we will see that in many cases this concept of entanglement is too narrow for our purposes and it doesn't capture all the idea of Schrödinger. Then, motivating this situation with entanglement, with the usual notion of entanglement, I will present a generalized notion that it was first proposed by Barnum and collaborators, and then discussed in a more general framework by other authors. And finally, I'm going to discuss some of our results when we go beyond entanglement. So what is quantum entanglement? As you know, it is probably easier to start by defining what a separable, non-entangled state is. And for example, if we have a bipartite scenario where A and B are these two parts, a separable or non-entangled state is one that can be expressed as a complex combination of product or non-correlated states. So this complex combination of product states gives our notion of entanglement, and it is probably the weakest notion of entanglement. We can have stronger notions that arise when considering the possibility of local hidden variable models or violation of value inequalities. But this definition here is going to be enough for our discussion, and it's the mathematically easier way to state the problem. And for pure states, the non-entangled states, the separable states, are just the product states. That is, the only separable pure states are the non-correlated ones. So, in the usual treatment here, there are equivalent statements to the previous one that try to define what a pure non-entangled state is. For example, we can say that a pure state, bipartite state, is separable if the subsystems are also in pure states, right? And here in some way we're recovering that idea of Schrödinger when he says that the knowledge of the whole entails the knowledge of the parts, right? In other way, we can say that a pure bipartite state is separable when the global state can be completely specified by specifying its parts. That is, we can compute the expectation values of local observables to recover the knowledge of expectations of the whole system, of the Schrein system, right?
Well, particularly you need that it's a product. So
sure.
if you know the expectation values of all local observables, for pure or mixed, it doesn't matter, entangled or not.
No, in this case, I am talking about pure states because if not, here we will have a combination of expectations, right?
I see. Okay.
So I'm specializing in the pure scenario because it is easier and it is enough for these notions.
But even in entangled, so just a sentence. Maybe I shouldn't interrupt you, but global state can be completely specified by the expectation values of local observables is true for any pure state.
Sure. For any pure state.
Yes, whether it's entangled or not. But
no, if it is separable.
No.
So no entanglement. This means
no. The left-hand side of your equation will uniquely determine any pure state.
Sure.
But the left-hand side of your equation will not always equal the right-hand side of your equation unless they're separate.
Sure. That's what I tried to say. Sorry.
That's okay.
I wasn't clear.
There's just a bit of a contradiction between your equation and the sentence. We'll talk later.
Okay.
So then we give you that one into specifying the balance.
So what happens when the state is entangled? Then, for example, in the case of a maximally entangled state, a Bartlett state, for example, or EPR-like state, if we know that the Schrein system is in this pure state, then we can compute the partial traces to obtain the reductions, the marginals, and we will see that the subsystems states are proportional to the maximally mixed state. And in other words, we can say that we are having total knowledge of the whole, but we know nothing about the subsystems in the sense. In the simplest scenario, when we have, for example, two 1/2 particles, two 1/2 spin particles, then this belt state here can be said to be locally equivalent to this mixture of product states, because if we are just allowed to compute expectation values of local observables, then we cannot distinguish both situations. You don't see that?
It's not true. That's
Right.
Again, so quantum mechanics has this unique property that if you know the expectation values, if you know the expectation values of tensor products of observables, then it uniquely determines the quantum state.
Yeah.
Perhaps you're saying this, that if you know the expectation values of observables in one system,
On one system,
and then you know the ones of the other, it doesn't uniquely determine. Is that?
I am saying only of local. For example, an observable only defined in A part or in B part. Then
okay, so you're not allowing in any looking at correlations.
exactly that. I am saying locally in that sense. I am only allowed to perform expectations in Alice or in Bob, but I'm not allowed to compute expectations that give me the correlations between both of them.
Okay.
Right?
Thanks.
In that sense, I am referring to local equivalent. If we are only capable of compute local expectations in Alice lab or in Bob lab, then I cannot distinguish both situations.
Okay.
Is it clear?
Yes, sorry.
No.
I misunderstood.
I think that the word local. Local in this sense is that watches only one part. I mean, an observable that only one of the parts.
I think we have clarification. So if I were to perform local measurements, and look at the correlations between outcomes, then I could redetermine it. But you're not allowing.
I'm not allowed to know the correlations between them.
Yeah. Thanks.
No. So we can rephrase the problem in the following manner. We can say that we have these two spin-1/2 particles, and we have an algebra defined by the local observable operators. That is the one spanned by the local spin operators here, right? So this, I'm sorry, it doesn't see very well. This algebra here can be said to induce the usual notion of entanglement, because, I'm sorry, this algebra here can be separated into local algebras, like the one of Alice, the one of Bob, and we can say, as I said before, that if we only compute expectation values in one of that local algebras, we are unable to distinguish a Bell state from a certain mixture of product states. The first question would be why we need to be happy with this algebra, why not another kind of algebra? For example, one could think of this kind of algebra here, where now these operators will tell me something about the correlations between Alice and Bob, right? So if I call this the relevant algebra for the moment, the nick doesn't work anymore. This is
Igual que sí, sí. Se escucha bien, se escucha bien.
So, if we are aware now of this relevant algebra, then we can see that every Bell state in the previous scenario can be looked as a non-entangled state when we measure these observables. And that is because, as I said, computing expectations of this set allow me to distinguish between a Bell state and certain mixture of product states, right? So, going deeper into the math, this local algebra induces a tensor product structure over my whole full Hilbert space, that is that one here. So this is in the ordinary non-relativistic quantum mechanics scenario. We can prove that the Hilbert space of the full system can be factorized in a Hilbert space of A and a Hilbert space of B, given that we have this local algebra. And for this other algebra, we have a different tensor product structure, right? I'm going to into detail later. So we can say that for this new relevant algebra, the Bell states with respect to A and B, the A and B partition, now can be written as product states. And so the reductions are pure and the global state can be distinguished from mixtures. Yes? But here we have new subsystems, and they are mathematically as relevant or as legitimate than the previous one. So from now on, I am going to talk about alternative observers to this situation, but I'm not ascribing to any kind of subjective meaning in this notion. I just say that we have an alternative observer when we have different relevant algebras compatible with a given system.
So for clarification before we go on, and this may just be the notation, but on the left-hand side you've got tensor product signs anyway, and in the previous one, the local algebra, you had tensor product signs, but it was always just the identity on one part. what's the relationship between the tensor product signs that you're using in the algebra and the tensor product signs that you're talking about in the Hilbert space? And I'm not quite seeing where you're starting from, because don't you normally think of the operators as being defined by their action on Hilbert spaces having a certain structure? But you're wanting to start with the observables and then use those to define different, or differently decompose the Hilbert space. But I just don't see what the relationship is between the tensor products signs on the left-hand side and on the right-hand side of the board.
I don't really see what you're saying. Here, for example, if I understand your question, this tensor product structure is defined in the Alice and Bob A and B scenario. So here I have this operator is associated to the spin in Alice scenario and the identity in this part, right? And
what space is that? Are those operators defined on?
In what spaces do they operate?
Yeah.
In this total Hilbert space in C4.
Okay.
In this case, because we have two spin one-half particles.
Right. And that C4 has a natural decomposition into C2 tensor C2, yes?
Exactly, yes. But here we have C4, and it can be factorized as C2, and here we have the same, but the degrees of freedom here, for example in this subsystem, mix the ones of Alice and Bob. So because the composition here is different from the previous one. We can have different decompositions in C2.
So really, on the right-hand side, would you put they're actually different tensor products?
Yeah,
Well, I guess you capture that by your
just a mathematical observation. In the right-hand side, they are isomorphic, and indeed they can be taken to be the same. But the important thing is that you are concentrating in different algebras and on the left side. So when you do that, that's different because the algebras that you are looking at represent the observables that you are concentrating on.
Okay, I'm not sure if you are convinced, but my idea is to go fast in this part because all this mathematical framework is developed in several papers of Barnum, Sanardi, so we can discuss better this at the finish of
Would it be helpful to say what Ari just said, which is that we're just focusing on different bases in the two Hilbert spaces. It's not really that you've got a different tensor product structure in the Hilbert space. It's that in the one case you're looking at an unentangled basis, and in the second one you're looking at an entangled basis. Is that okay?
Yes, I think that is an equivalent viewpoint.
Yeah, fine. Let's sort to hold things up. Carry on.
So, we can define alternative subsystem decompositions for the same problem, and these alternative subsystem decompositions is going to give different values of entanglement for each state of the Frank system. And this would be our first observation. There are multiple possible decompositions into subsystems compatible with the given system. Right? Probably the most naive approach would be to consider a given subsystem decomposition and a more coarse-grained decomposition, for example. I don't know if you see the difference. So let's move on to another example that is in the identical particles scheme. And it is probably the most controversial chapter in the entanglement book because we know that when we have identical particles, if we need indistinguishability, then, for example, for n identical fermions, the Hilbert space of these n identical fermions is given by the anti-symmetrization of the n-fold tensorial product of Hilbert single particle Hilbert spaces. And here there is no tensor product structure. You want this variabilization. And in principle, it's difficult when you have some systems, and even the partial restoration is not well defined. Nonetheless, there are in the literature many attempts to measure entanglement in these settings, but in general there is no unified framework for all the identical particle situations. But there is, we can see the following example. Let's suppose that we have two fermions here, and we are going to use the Jordan-Wigner mapping to map the state space of the two fermions with the state space of two spin 1/2 particles. For example, the 0,0 state with two spins down, and it's going to be the vacuum with no fermions. The 0,1 state would be the state with one fermion in the first mode. So here we have the creation operators. And with this prescription, these Bell states in the qubit or in the two spin 1/2 particles scheme becomes these two states in the fermion framework. Then we can assume further that we are in a physical scenario where the number of fermions is conserved. That the physical process, for example, where the number of particles is a constant quantity, then the admissible observables must be those that commute with the total fermion operator. And it is straightforward to see that these bilinear fermion operators here commute with the Lie algebra for the unitary group of degree 2. Right? So it is somewhat natural here to say that this algebra is in some sense a natural, relevant, observable setting to contemplate this system. But the first problem here is that this algebra here does not induce a tensor product structure over the Hilbert space of the two fermion space, of the two fermion system. So here we have no subsystem identification in principle. But anyway, we can recover some notion of entanglement if we remind the works by Schrödinger in the second slide, because given this prescription here, the first two states are combinations or superpositions of states with one fermion, while the two states at the bottom are superpositions of the vacuum with the two fermion state with two fermions. Then our relevant observer here is unable to distinguish between this state and certain mixtures of product states, in the sense that I have previously explained. If we just compute expectation values of observables that commute with the total fermion operator, we are unable to distinguish this state here from certain mixture of product states. So in that sense, we can say that the first two states are not entangled, while the latter are entangled. But we can go to another scenario where we consider, for example, the non-mode entanglement. And the mode entanglement framework is equivalent to the local spin algebra framework. And in that case, both the four states are mode entangled. So what we should learn here is that it is not enough to say that a state is entangled or not. In this case, we can say, for example, that the first two states are omega relevant entangled, and the last ones are omega relevant entangled. And this would be our second observation. It's possible to define a weaker notion of entanglement without relying on correlations between some systems, but instead it is necessary to select a relevant observable algebra. So here in this second stage, in the road to relativize the notion of entanglement, we have a radical change, because we are not speaking anymore about correlations within subsystems. We even don't need subsystems here. We just need a relevant subalgebra of the total system algebra. And in that sense, I say that we have two stages in this relativization process. First, there are multiple possible subsystem decompositions, and then we can have a notion of entanglement even without the subsystem decomposition. So these ideas were formulated first by Bartlett and collaborators, and they said that entanglement can be seen as the relative mixedness under restricted capabilities, where the restricted capabilities are given by the relevant subalgebra of operators, and the relative mixedness here is computed, for example, projecting, there is a mathematical rigorous formulation here, we can project the joint state, the state of the full system, into this subalgebra of operators, and then we can compute the purity of that state. So if we start with a pure state, so we have total knowledge in that sense, if we then compute the purity of the projection, and we can say if we have entanglement or not. And they applied this framework to different settings, for example, to complex operational models or general probabilistic theories, the Hermitian closed operator subspace, or the associative algebraic setting. And then Balachandran on one side and Benati on the other hand extend these ideas, going deeper into their implications in the identical particle setting. And for example, Balachandran says that we have to compute the state restriction to a given subalgebra, and this state restriction is given by the GNS construction. So we can have this state restriction. There is a sort of extension of the partial trace operation in the usual entanglement setting. And once we have this state restriction, we can compute the purity again and do the same as before. For example, in ordinary quantum mechanics or relativistic quantum mechanics, we can start with a given algebra of operators acting on a certain Hilbert space that identify our system, and we have our state given by an expectation value functional over the space of observables. So to define this generalized entanglement, we need a relevant observer to be defined. Then we compute this restriction or projection over the relevant observer algebra, and we compute the purity relative to that restriction. And we can recover the usual notion of entanglement in the case that this relevant algebra induces a tensorial product structure over the full Hilbert space here. Because in that case, we can talk again about correlations between subsystems. This happens when we have at least the following two conditions. We need to identify two subalgebras here, for example, the Alice and Bob subalgebras of operators, and the minimal algebra that contains both must be contained in the full algebra. This is some sub-completeness condition. And then we need an independence condition, and it can be achieved, for example, if we ask for mutual commutativity of the operators involved subalgebras. There are other ways to ask for independence in probabilistic and statistical scenarios, but this could be one. So far it seems that we can generalize entanglement with no many troubles, but there are many issues in this new notion. For example, we have said that we have a multiplicity or maybe infinite possible relevant subalgebras. So is there any preferred subalgebra, any preferred observer? Well, the few authors that go into this discussion adopt different attitudes. For example, Zanardi says that local accessibility or experimental accessibility should be the guiding idea to select the preferred set of observables. And in turn, Harshman says that the symmetries and dynamical invariances must dictate what are our preferred observers. And Earman says that this debate can be put into a realist versus a pragmatist debate, where Zanardi plays the role of the pragmatist here, and Harshman of the realist, maybe. And Earman says that he oscillates between the two positions.
Do they actually give different answers then?
Yes.
Might just be, okay,
Yeah, sure. For Zanardi's position, for example, will be different in different stages of the science, because what is locally, what is experimental accessible today is not the same that 10 years ago, for example, right? But it is interesting to know that if we have our system and our collection of possible relevant observers, and we want to select a preferred one, I think that we need a third actor to come into the play. For example, the Hamiltonian in the Harshman framework, to say which are the dynamical invariances of our system. Another issue here concerns the convexity of the space of separable states. In the usual notion of entanglement, the separable states form a convex set into the larger convex of all the possible states of our system, and it is closely related to the possibility of having entanglement witnesses, and in turn with the possibility of defining Bell inequalities here. But in this generalized framework, it can be proved that almost all states are generalized entangled with respect to any observer setting. So it seems that this convexity is lost, but for example, if we pay attention only to one observer, omega 2, for example, the separable states with respect to this omega 2 observer in this generalized notion is easy to see that it still is a convex set. And the same happens for another omega 1 observer. Then we can, for example, define entanglement witnesses with respect to observer number 2, the same for number 1. So this entanglement witness associated with a hyperplane where all the separable states remain in one semispace, right? So yes, we can recover this convexity if we fix a relevant algebra. There are also many interpretative issues here. One, for example, regards the decoherence-assisted classicality of the theory. You know that decoherence is one of the most popular ideas today to explain the classical limit in some sense. It was pointed some years ago by Olympia and Sebastian that decoherence is a relative concept, because we can have, if we weaken the notion of decoherence, we can define a new perspective where some observables decohere while others not. And we don't need to speak here of the diagonalization of our density matrix in a certain pointer base. And at the same time, Dubich, for example, and collaborators talk about parallel occurrence of decoherence. Lychkovskiy says that we have a relativity of decoherence classicality in the same sense. There are, for example, many possible subsystem compositions, and not the composition So my third observation should be that this relative character of generalized entanglement does not imply any ambiguity about the concept, but what we need instead is to consider this relative character seriously. We can say, for example, that generalized entanglement is some kind of relational property between our system state and a given relevant observer. So given a state of the system and a relevance of algebra, there is a unique value of generalized entanglement, and there is no ambiguity at all in that notion. As a result, I'm not going into details, but as I said before, we have entanglement, generalized entanglement in almost all states, because we can define suitable relevant observers to find generalized entanglement almost in every quantum state. What happens when we go beyond this chord? Well, there are many roads we can follow from here. I am going to specialize in the discord case, that is an information theoretic measure that tries to distinguish between classical and quantum correlations. Discord can be thought in different ways. For example, we can say that a non-discordant state is a state where the information of the giant system can be acquired locally by a local part of our system. So we are speaking again of bipartite system. We have Alice and Bob, and Alice can perform local measurements, and these local measurements allows her to acquire information of the giant state. And in the same manner, we can say that she can perform a local measurement that is non-selective, and in that way she doesn't disturb the giant state of our system. So the non-discordant states mathematically can be expressed as convex combination of the tensorial product of local projective orthogonal measurements. And we can see from here that non-discordant states, or classically correlated states, are also separable states, right? And the main ingredient here is this bilocal measurement. If we want to give a certain measure of discord, quantitative, we have to distinguish between the pre and the post measurement state, for example, using the mutual information or any geometric measure of distinguishability. And there are many differences between discord and entanglement. Maybe one of the most important ones is that the non-discordant states, the classically correlated states, doesn't form a convex set like the separable states. For example, in this picture, taken from the work by Ferraro, we can see that in gray we have the separable states here that forms a convex set, while these black lines are the non-discordant states. That indeed they form a set of null measure, zero measure in the set of all the possible states. And there are two consequences closely related to this non-convex structure of the non-discordant states. First, there are some discordant states that have discord, that can be extended to non-discordant states, preserving the localities. I'm going to explain this first point in a minute. The second consequence is that discord-like correlations do not obey the usual monogamy relations that we know from the entanglement framework. So, I'm going to say a couple of things only about how to generalize discord as we have done with entanglement. We saw that entanglement has two stages in this relativization process. The first concerns the identification of multiple possible subsystem decompositions, and the second stage, the deepest one, says that we can even have entanglement without correlations, without subsystems, and entanglement accounts for the relative purity and the restricted capabilities. In the same sense, we think that we can speak of discord as a kind of quantum peculiarity that accounts for the relative coherence and the restricted capabilities. I'm not going to explain this better now, but we can discuss this point later. I just wanted to say that there are a couple of measures that we can find in the literature, like the local quantum coherence, local quantum uncertainty, that maybe are good places to start seeking for this generalized discord. So, regarding the first point, when I said that discordant states can be extended to non-discordant ones, in the entanglement framework, we know that if Alice and Bob shares a shunt system in a separable state, like here, and if we see that Alice's system is a composite, or perhaps she has many degrees of freedom, and we trace over some of these degrees of freedom, the result is going to be a separable state too. So we start with a separable state and tracing out some degrees of freedom locally in Alice, for example, we obtain a new separable state. So if omega is AB separable and entangled, then omega is equal B entangled. But in this core scenario, it's rather different. We can start with the classically correlated state, and if we do the same, we can end up with a discordant state, because the reduction of this projection here are not necessarily new projectors in this reduced state. So if rho is AB not discordant, it doesn't imply that rho is A1B not discordant. This result was first pointed by Lee and Luo in 2008. They say that every separable state, and here in separable, it is contained the set of discordant separable states. So every separable state is formally the reduction of a classically correlated state in a bigger Hilbert space, preserving the original partition. This separable here is very important because if we reverse our process of reduction and we do the reverse exercise, we can see that we are starting with a separable state and we are obtaining a classically correlated state. So this result here was poorly explored in the literature, but we obtained a couple of other new results there. We saw that Luo's proposal to do this extension of a separable state is not optimal, so we can have another extension algorithms that are better in the sense that we can start with a given separable discordant state and obtain some classically correlated state in the space of less dimension that it is possible. And for example, in particular, a maximally discordant separable state of 2 qubits can be extended to classically correlated states, adding a single qubit. In this sense, we also say that any quantum task carried out using non-entangled states can also be undertaken using classically correlated states. And this result is important because it is growing evidence in the literature that discordant separable states could be a genuine resource for quantum computing. And what we do is to apply this idea in the remote state preparation scenario, that is a variation of the teleportation protocol, and in the entanglement distribution framework. So my conclusions would be the following. First, the quantum correlations are relative concepts, and there are two different stages in this relativization process. I put correlations between quotation marks because in the second stage we even don't need to speak about correlations. This relativity does not imply ambiguity at all if we take seriously this relative thing. And this second point answers one of our questions at the start of the talk. Then, regarding the consequences of this relative nature, there are many, but we saw, for example, that the classical appearance given, for example, by the decoherence process is relative to one of these observers too. And my first open question should be, what happens with the concept of information here? Is in some way this relative nature of quantum correlations transferred to the concept of information? And I think here that the answer should be rather different depending on our interpretation of the concept of information. It's not the same if we ascribe a physical interpretation of information or a deflationary view, probably. And finally, what other quantum resources can be obtained? How we rely on the quantum state-space dimension. We saw that we can start with non-discordant states in big Hilbert spaces, and preserving the localities, we can obtain discordant states. The same cannot be done with entanglement. So, what other resources, more than discord, happens to this same fact, the same phenomenon? So, thank you.
Good. So we have 10 minutes for questions. Dan.
What if your Hilbert space is of prime dimension? And you just live in the Hilbert space of prime dimension?
Well, if the dimension of our Hilbert space of the full system is prime, then we surely can have a factorization into smaller Hilbert spaces. So we have not a naive interpretation in terms of subsystems here, but we can, in that case, define relevant operators of algebra, like I said before, and we can have a notion of entanglement even in that case. I don't see why not.
And then you are taking a subspace at the beginning of the process. Just looking at
A subspace.
A subspace of non-prime dimension, and then you play the whole game.
Exactly.
It is a price you have to pay always to remove part of this. Now my point is precisely that you are relativizing entanglement, and I love it, and still you have to relativize something else, because you still play in tensor protocol all the time.
No, in this second stage, we are not playing precisely with tensor product structures, because we just define a relevant algebra of observables, and we don't need to tensor product there. All this can be done just relying on the algebraic approach without Hilbert spaces at all. For example, in the Balchandran perspective, he only uses the algebras, and he speaks about this state restriction given by the Shiena's construction, but he don't need Hilbert spaces.
Olympia?
It's not a question. I would like to make it perhaps a more conceptual or philosophical comment about this view and that is related with other views we are developing in our group, in the interpretation of quantum mechanics and in decoherence. Perhaps there are two different approaches. A bottom-up approach where you suppose that you have elemental systems and then you have the Hilbert spaces and then you combine to obtain composite systems. So you are always in a framework of Hilbert spaces and tensor products of Hilbert spaces. But I think that this approach and our decoherence approach and our interpretation is a top-down view where you begin by the whole closed system, and you can conceive it in algebraic terms. So you think about the algebra of observables, and then you ask yourself, in many ways you can describe from which perspective. The perspective is given by the set of observables, and you can describe it in from different perspectives. So I want to point out to the different perspective. I mean the different view, the bottom-up versus the top-down.
I have a naive question about discord. I may have heard you wrong, but did you say that the non-discordant states have a set of measure 0 in state? So then, and this is the naive question. So if you've got some distinction, which is a distinction between, well, in which, for all practice, well, you can just say almost everything is of one kind. Why is it an interesting distinction? It looks like if you're going to have an interesting distinction, you want to have, here's a bunch of things which are on one side, here's a bunch of things which are on the other side. But if almost everything apart from a set of measure 0 is of one kind, why have the distinction in the first place?
Yeah, that's an interesting remark. I think that it is not as important the distinction between non-discordant and discordant. What is most important is to see what discordant states are closer to the non-discordant set, although it is of 0 measure, right? So we can define a distance from the non-discordant state to all the other states and see which of them are closer.
Okay, so it's to do with it's some kind of distance measure as opposed to a sorting mechanism of one into another kind. Okay,
that's my view.
Yeah, that's helpful.
Just a remark here. This paper of Zanardi was probably the first when he talks about different subsystem decompositions, and he talks about virtual subsystems here, where the virtual subsystems are the ones that, in principle, are not experimentally accessible. And then here they develop this idea of entanglement without subsystems, and these other works are also interesting in the subject.
Good. So Chris had a question. Chris has a question.
So the notion of discord, it looks like it was dependent upon which information function you use. So you get a discordant set and a non-discordant set with respect to a choice of an information function?
No. The non-discordant states, no matter what,
no matter what
information theoretic measure you use,
okay,
is the set of states that can be expressed as a convex combination of local projective measurements. It is always the same.
That's always the same. Okay.
If we choose another measure, you are going to obtain different scales, probably, of your discordant states.
Okay.
So in answer to my question, you said it's the distance away from the non-discordant that's interesting. and then one could use, it's an arbitrary choice of measure, which it is, but again that might look like a problem. It'd be nice if there was some neutral way of stating what, say a non-metrical, maybe some order theoretic relation which, with respect to which all of the information, all of the possible information measures one might use would be tracking those order theoretic features. Because that's more like a robust component of reality. I had a final thought. So, of course, for a very general case, it's helpful to go to the very abstract algebras and representations, theorems and so on. But if you're just starting with ordinary non-relativistic quantum mechanics or non-relativistic field theory, then you don't have to go to the algebras. But it looks like you can make your same key points without doing it, without having to invoke the very abstract C-star algebraic way of doing things.
It is not necessary, but maybe it can be a good starting point because it allows you to see the problem from other perspective, and it can be useful then to transfer that results to other theories.
If I understand, at least Zanardi's interest in this, we might have said, well, we define tensor product is naturally defined by saying that I can work on this system, subsystem, and I can work on this subsystem easily. Independently, easily, these are easy operations for me. But the reason for the generalization might instead be something else. It might be that, for instance, I can perform sigma x easily and sigma y easily. Well, I don't want sigma x and sigma y, but two observables and the associated unitaries, that I can get from some Hermitian operators, I can perform those easily, but other ones I can't.
Yes.
And so that generates a subalgebra that's not equivalent to a tensor product. So in the laboratory, the experimentalist says, I can perform these things easily. And then you generate an algebra from the things that we performed easily. And then with respect to that subalgebra, which is not just breaking into tensor products, it's something different than tensor product.
That is the particular example.
Then you can define entanglement with respect to a subalgebra and discord represented with respect to a subalgebra and so forth. So there really is a necessity, I think, for thinking about this stuff, at least from the pragmatic perspective. And I don't think that it's just a question of trying to be more abstract. Okay. There are more interests. Beside the tensor products, the algebras that define the tensor product, there are also other subalgebras that are interesting, but don't give a tensor product.
Okay, that's right.
For example, the identical particle setting is one of that sense.
Right.
Let's thank the speaker again.